the are with the PAs. So I don't have the physical examination workbooks. Go to the PA, to Michal or to Tomer, and you'll find it in their offices. All right, so we have finished the Fermi fluid last week, and I just want to remind you what is the result that we obtained. So the particles are fermions, and what we have seen that at low temperatures, so this is the energy, at low temperatures what happens is that all the different particles are basically sitting one on top of each other. We assume that the particles are completely independent, they don't care about each other, and the particles are free, saying that they only have kinetic energy. Now, to say that they are free, are not interacting, is basically to lie to you, because according to quantum mechanics and Pauli exclusion principle, they are always interacting, right? So this is why we got this specific structure, because two particles cannot occupy exactly the same state. This is why they're all, topping one top of each other. And what we have found that they are filling up the energetic spectrum up to an energy, well, let's say, which is T multiplied by K Boltzmann. This is the energy, or the Fermi energy, where the effective temperature, the effective, is on the order of 10 to the 4 up to 10 to the 5 Kelvin. So this is what we obtain for completely free particles not interacting up to Pauli exclusion principle. And then, so the final note of the last lecture, I said, well, because we have such a huge effective temperature, or such a huge Fermi energy, we don't really care about interactions of those particles. And I want to a little bit strengthen this point and explain why do I say that I don't really care about interactions. So why this number was so big? This number was big because we had many particles. And this number was large. So we took a chunk of metal and we looked how many electrons or charge carriers we have inside. We assumed that they're fermions, and this guy was on the order of 10 to the 23. And because of this 10 to the 23, this is the big number. This gave rise to this another big number, which is the effective temperature. Okay. Now, why then I don't care about interactions? Because this effective temperature, it basically describes the effective temperature or the energy, and this is only kinetic energy, of all the particles that are in the vicinity of Fermi energy. Okay. So if you remember, when I plot the occupation probability, as a function of energy, it has this specific sigmoid shape. So it is around 1 for low energies. Then it crosses somewhere the sign of 1/2, explicitly when the energy equals to the Fermi energy, and then it decays to 0. Okay. And what we have shown that this specific only particles that are having energies in the vicinity of what? In the vicinity of mu, only those particles are participating in anything inside the system. All those states states, it's not particles, I'm sorry, are only the states. So all the states that have energies far, far below mu, they always filled, and the probability that they are going to be occupied and then unoccupied and then occupied and then occupied is exactly 0. They are always occupied. All those energies that are far above mu are always unoccupied. So nothing dynamically happens over there. Okay? They are always empty and there are no particles sitting in the energetic states where the energy is much, much larger than mu. So anything that happens in the vicinity of mu. Okay? And this is on the order of K Boltzmann, the temperature of the system. Okay? Not mu, but the effective temperature, but the true temperature of the system. Now we're speaking about low enough temperature, so our temperature is pretty low. Okay, so this temperature is pretty low. What is mu? Mu is on the order of T effective. Okay, so this value over here, it is something like 10 to the it's a big number, which corresponds to 10 to the 4 or 10 to the 5 Kelvin. Okay. Now there is some small variations about this number, so some energetic states that can be occupied and unoccupied. Basically states where the occupation probability is neither 1 and neither 0. Okay. So what is those energetic states that contribute to something? Any other states do not contribute because they are always occupied or always unoccupied. So those states have energies, kinetic energies, no potential energy, which is extremely large. Okay. 10 to the 4 or 10 to the 5 Kelvin. Now, if I add some interactions, it will modify or it will add potential energy. So far, I only had kinetic energy. I will add interactions, I will add potential energy. When I add potential energy, it's going to modify my total energy of each of those particles. But the kinetic energy is large, right? So all those states, or all the particles in those states, have extremely large kinetic energy. 10 to the 4, 10 to the 5. So it's not important if I perturb the system and add some interaction. I need to perturb it extremely harshly. Okay? I need to include some very extremely strong interactions, strongly to correlate those particles in order to affect somehow the kinetic energy. Basically saying, because all the particles are on top of each other, eventually only the particles that are important are the particles that are sitting at the top. Those said particles have extremely large kinetic energy, and potential energy is not important. So I can add some potential energy. It won't affect those particles a bit, right? So if I have an extremely massive particle or particle with extremely large velocity, I add to it some small potential energy. We don't care. This is what happens over here. Okay? So this is why I don't need to include, at least at low temperatures. Okay? When I increase my temperature, something else has to happen because I will have more and more states that are going to participate. Okay? So at large temperatures, it's already not so simple what I'm trying to say to you. But at low temperatures, it is indeed true. And I don't really care, okay, for this Fermi gas. I don't care about interactions. As long as this effective temperature is high, and it is always high when I have huge number of charges that participate in the game. When my system is small and the charges are correlated, I won't get a large Fermi energy, and then all this claim is not going to be valid. Okay? So it's only valid when n is large, and then I don't really care about interactions. And Fermi gas actually describes pretty well different metals that we have. Any questions about that? All right. So if you have no questions, we're going to describe now. If we treated Bose Fermi gas, we are going to treat Bose. So this is gas or fluid. We're going to take care now of Bose gas or fluid. Now, what's the difference between fermions and bosons? Fermions do not occupy exactly the same state. Bosons, well, they don't care. Okay? So the Pauli principle does not apply for bosons, and we have to treat it somehow differently. Now, we can start with a simple example, okay, of, let's assume that I have three states. I have epsilon 1, and I have epsilon 2, and I have epsilon 3. Okay? It's exactly the same as we started with the Fermi fluid. Before treating huge number of states and huge number of particles, we look on the system, three-level system, and we try to explain what happens in the system. Now, we use exactly the same formalism as we used for the Fermi gas. Meaning, I want to describe everything as non-interacting picture, but not non-interaction pictures of different particles. I want to describe it as a non-interacting picture of different levels, right? Because I need to count or to produce to you the partition function. For the partition function, I need to count on all the different states, energies of the system. And since the energies of the systems are simply the sum of energy of level 1, and energy of level 2, and energy of level 3, okay, it is an additive function. And all the different levels, they don't care about each other. Okay? We explained it last week. Now, what is the main difference between Boso and Fermi description? If previously, if I would put a particle, this state up over here, I couldn't add another particle at the same level. I had to push it into level number 2 or level number 3. But because I'm talking now about bosons, I don't care how many particles I can put exactly at the same level. It can be 1, 3, 4, or 47. Okay? So there are no constraints about the number of particles that can sit at the same level. So this is a big difference. Previously, we had a counting statistics of 0 particles or 1 particle. Now we have 0 particles, 1 particle, 3 particles, etc., etc., etc. Okay? So let's see how it works out for the partition function. Now, the partition function we use to calculate it, we use the grand canonical formalism. Yes?
We assume that we can differ between the bosons, or does it matter?
Does it matter?
If you have an n factorial in the...
Do I need an n factorial now? No. No. So the answer is no. Where I'm getting this n factorial, remember, where I'm getting this n factorial. It's a classical description, but I don't know if it's fermions or bosons, and I count particles, and then Gibbs invented this magic trick of basically saying, well, I don't get a I don't get a linear growth of the free energy. Okay? And this is where this n factorial came from. So it's a trick to extrapolate between the fermions and the bosons. But when I'm treating explicitly boson system, bosons, and in physics they are always indistinguishable. I don't know if it's A and B. So it's only important when I know that here's particle A and here's particle B. I shut my eyes, and after I shut my eyes, I don't know who is A or who is B. Right? So in classical mechanics, I can always know who is A and who is B. In quantum mechanics, it's not impossible. It's not possible. Great. So we're working on grand canonical description. Basically states that we have a partition function, and for this partition function, we sum over all states e to the power minus beta ei minus mu ni. Okay? So each state is described by the energy and the number of particles at this specific state. Exactly as we did it for fermions, as was done for fermions, it is states or energies of epsilon 1, energies. שלום.
עם הביטחון, יש פה מזוודה במסדרון, שייכת למישהו?
A suitcase in hall? Someone's?
אוקיי.
No. Energies of epsilon 2. Energies of epsilon 3. Okay. And here I will have e to the power minus beta n3 epsilon n1 epsilon 1 minus mu n1. Here I have e minus beta n2 epsilon 2 minus mu n2. Here I have e to the minus beta n3 epsilon 3 minus mu n3. Look on those terms. So what exactly I have done? I've said the following thing. Energy is n1 multiplied by epsilon 1 plus n2 multiplied by epsilon 2 plus n3 multiplied by epsilon 3. And each energetic state is described by a specific number n1, n2, and n3. And I also described explicitly by n1, n2, and n3, which is n1 plus n2 plus n3. Now for fermions, n1, n2, and n3 could get only numbers 0, 1, 0, 1, 0, 1. Here they can get 0, 1, 2, 3, 4, 5, 6, 7. So n 1, 2, 3 is 0, 1, 2, 3, etc., etc., etc. But the independence of n1 and n2 and n3, okay, and the way how we describe or have written the form of the energy, which is a sum of the energy of energetic state number 1, the energetic state number 2, and the energetic state number 3, it allows us to write the partition function in a factorizable way. Okay. Yes?
E of I represents per state.
E of I represents the state of the system. So the state is, for example, this is the state of the system. Look on this. The state of the system is energy is 3 multiplied by epsilon 1. Where is n1 equals 3, n2 equals 0, and n3 equals 0. This is the state of the system. Okay. This is a specific state of the system. Now, since I have degeneracy in my system, right, because I assume the bosons can get spin up and spin down, so here I would write the degeneracy. So
not always.
let's write it down as G0, G0, and G0, and G0 is degeneracy of the energetic level. So you're right. I don't know what the degeneracy is. Maybe my system, my bosons only have spin 0, and maybe my spins can have spin 0 and 1, and maybe they can have spin 0 and 1 and minus 1. In general, this is G0. Now, since the energies do not depend on the value of the spin, unless we have a external magnetic field, but we don't have external magnetic field. So, since the energies, energetic states, are not split due to the external magnetic field, the spin is not affecting the energy. Basically, those partition functions for each state, they are multiplied by G0. Why? Because basically each state I have epsilon 1 with spin up, and I have epsilon 1 and spin down, for example. And since they are exactly the same, it's going to be contribute as a multiplicative factor over here to some power. We've seen this in fermions. It's exactly the same way as we derived this equation for fermions. Exactly the same works for bosons. The only difference is this n. In fermions, you can have 0, 1, and here we have 0, 1, 2, 3, 4, 5, infinity. Okay. Now that we have written down, we can say that the partition function is simply z1 to the power of g0 and z2 to the power of g0 and z3 to the power of g0. How we compute? Let's compute, for example, z1. What is z1? So z1 is this guy, all the different energies of epsilon 1. Since epsilon 1, or the different energies of epsilon 1, are defined by n1, I can simply sum over n1. n1 goes from 0 to infinity, e to the power minus beta. Here I have the energy, which is basically n1 multiplied by epsilon 1, minus mu n1. Okay. And now I have to sum, and it's a very easy sum, for all the different n1s. Let's write it down as sum n1 equals from 0 to infinity, e to the power minus beta epsilon 1 minus mu, all of this to the power n1. So this is a geometric series. n1 goes from 0 to infinity. The first term, when n1 equals 0, it's simply 1. So I have 1 divided by 1 minus e to the power minus beta epsilon 1 minus mu. So this is z1. I do the same for z2, and I will obtain 1 over 1 minus. The only difference between z1 and z2 is this energetic, the level of the energetic state. So e to the power minus beta epsilon 2 minus mu. I do the same for z3, and the only thing that matters is the value of the energy for this specific level. It's going to be 1 over 1 minus e to the power minus beta epsilon 3 minus mu. Now, in order to write z, I have to take the g0 power of each of the states, and I have the total description of my system, because the moment that I have the partition function, everything else is somehow related to some kind of derivative of this partition function. It's like in probability, if the moment that you have the probability density function, you should know everything. And we know that z equals to 1 over 1 minus e to the power minus beta epsilon 1 minus mu to the power of g0, 1 over 1 minus e to the power minus beta epsilon 2 minus mu to the power of g0, multiplied by 1 over 1 minus e to the power minus beta epsilon 3 minus mu to the power of g0. That's it. Now, if I want to compute, for example, anything, right? I know that the grand canonical potential is minus 1 over beta log of z. And if I remember my class on thermodynamics, I can take some sort of a derivative of psi with respect to beta, with respect to mu, with respect to something, and I obtained everything that I need to know. Or, as I told you, there is always a different path. For example, if I want to compute the average number of particles, the average number of particles at the system. Okay. So it's either I have to take this minus d psi to d mu, okay, as thermodynamics prescribes, or if I don't like to take those derivatives, I can do the following, which is basically analogous. I can say, well, what is n? N is n1 plus n2 plus n3. Okay? So the total number of particles at the system, and the number of particles at level 1, the number of particles at level 2, and the number of particles at level 3. And I have to take an average of this sum. Crucial thing to remember for probability is the average of a sum. It's a sum over averages. So this is n1 average plus n2 average plus n3 average. And I need to compute the average for each different state. What is N1 average? I can go and describe it by using Z1 or using the definition. So it is N1 goes from 0 to infinity, N1 Fn1. Okay. So the average is the value of Fn1 multiplied by the probability of getting N1, summing over all the possible values that N1 can get. What is this Fn1? Since we're using grand canonical potential, it is e to the power minus beta N1 epsilon 1 minus mu N1 divided by Z1. Okay, we can take Z1 out, and we have 1 over Z1, as sum N1 goes from 0 to infinity, N1 e to the power minus beta N1 epsilon 1 minus mu N1. Okay. Now remember, for canonical ensemble, we always use the Feynman trick. Exactly the same goes here. We use the same Feynman trick. We look on this guy and we say, well, if I have N1 over here, and I have beta, and I have N1, so if I would take the derivative of this guy with respect to what? To mu. So let's look on this. If I had e to the power minus beta, N1 epsilon 1 minus N1 mu, and I take a derivative of this with respect to mu. D to the mu, it is what? When I take a derivative with respect to mu, what I get? Beta N1 e to the power minus beta N1 epsilon 1 minus mu N1. Right? So, you see, I can write N1 e to the power minus beta N1 epsilon 1 minus mu N1 as this term over here. Okay. So this is this part. I have 1 over Z1 as sum, N1 it goes from 0 to infinity. Now instead of N1 e to the power minus beta N1 blah blah blah, whatever I have here in the power of the exponent, I'm simply writing using this expression, which is 1 over beta d to d mu e to the power minus beta N1 epsilon 1 minus mu N1. I'm taking 1 over beta out of the sum. I'm taking 1 over d to d mu out of the sum. Okay, so this is the Feynman trick. 1 over Z1, 1 over beta, d to d mu. And I here have N1 goes from 0 to infinity, e to the power minus beta, N1 epsilon 1 minus mu N1. What is this sum over here? The partition function. So I have 1 over beta, 1 over Z1, d to d mu of Z1. And what do I obtain over from here? I obtain this as 1 over beta log of, d to d mu log of Z1. How it sets with this formula that I have written over here? It's the same. But why I have a minus over here? Because I have a minus over there. Okay. So don't get confused. Okay. If you have a minus or don't have a minus, it depends on what you're looking on. If you're looking on the grand canonical potential, you have a minus, so it's going to be minus d psi to d mu. Here I don't have a minus, It's just the d to d mu of the partition function. So this is what? This is n1. I can go and compute exactly in the same fashion n2 and n3 and n4, and the only thing that I need to know is what are the different z1s. Now, this I can take this derivative of this guy very simply, because what is z1? So d to d mu of log of z1 equals to d to d mu of log of 1 over 1 minus e to the power minus beta epsilon 1 minus mu. Okay. And it equals to 1 over minus d to d mu log of 1 minus e to the power minus beta epsilon 1 minus mu. Okay. And it is minus 1 over 1 minus e to the power minus beta epsilon 1 minus mu, and I have to take the inner derivative of the exponent to the power minus beta epsilon 1 minus mu, which is
beta times that.
so I have it
Minus
is
beta with minus
minus e to the power minus beta epsilon 1 minus mu multiplied by beta plus beta. Okay, so I have a minus from here, I have a minus from here, and in total I obtain beta e to the power minus beta epsilon 1 minus mu divided by 1 minus e to the power minus beta epsilon 1 minus mu. Or I can write it down as beta multiplied by 1 divided by epsilon beta epsilon 1 minus mu minus 1. So this is n1 average.
stuff.
Yes.
I need to divide by beta.
I need to divide it by beta. Right. So this is,
This ground of
okay,
the
let's write it down. So n1 average is 1 over beta multiplied by beta divided by e to the power beta epsilon 1 minus mu minus 1.
You didn't need to erase the beta in the כאילו שורה פה.
I had a beta, yes. And now I have 1 over e to the power beta epsilon 1 minus mu minus 1. Questions? Yes.
The GFS should be.
Yeah, wait. We'll get to the G0 in a second.
Yeah.
All right? You're right. There is a G0. We'll get it in a second. Okay. So this is a math. And before we get to the G0, do you remember what is, so this is bosons. N1 bosons. The average number of particles when we are treating bosons is 1 over e to the power beta epsilon 1 minus mu minus 1. If you're treating fermions, do you remember what's the average number of particles that we had at the level epsilon 1?
It's the same bottom with a plus.
With a plus. 1 e to the power beta epsilon 1 minus mu plus 1. So, first of all, there is a crucial difference between bosons and fermions. Fermions, we had only 0, 1 particle. So this N1 is also the probability of having exactly 1 particle at a level epsilon 1. For bosons, it is very different because the number of particles can be 0, 1, 2, 3, 4. There, it's actually unlimited or unconstrained. But we also notice crucial difference. It's a small difference between bosons and fermions, but it's actually very crucial. Plus and minus over here. Okay. Basically, because here I have a plus and an exponent is a positive function, nothing really bad can happen to n1. Okay. It can be a number from 0 to 1, and nothing bad can happen for the average number of particles that are occupying a single level when we're treating fermions. But we have here a -1. Okay? When we have here -1, let's look on the denominator. So we have e to the power beta epsilon 1 minus mu minus 1. So first of all, we know that the average number of particles that can sit at a given level have to be a positive number, or at least equals to 0. It can equal to 0, well, maybe, but it has to be a positive number because I'm counting particles. It cannot be -3. Right? There is no such thing as -3 particles, at least in this part of physics. So what it means, basically means that epsilon 1 minus mu is greater than 0. So epsilon 1 is always greater than mu. If you remember, for the chemical potential in fermions, the chemical potential, which was also the Fermi level, it was some level in between. It wasn't the lowest energetic level, it wasn't the highest energetic level, it was the level that described what are the energies that are participating in the dynamics. What are the relevant energetic scales that we need to take care of? Okay? This was this mu for fermions. But in bosons, the chemical potential is something really different. We see that this mu, it has to be lower than epsilon 1. And I don't really care what epsilon is. It's epsilon 1 or epsilon 2, epsilon 3. It's going to be exactly the same result. So for bosons, the chemical potential is always below any energetic scale that we have inside our system. Right? So it's a very different property. Somewhere in between on the energetic spectrum for fermions, below any possible energy for bosons. And this guy is restricted between 0 and 1. Here, when mu, and you remember mu can be modified as function of temperature. So in general, when mu is getting closer and closer and closer to epsilon 1, let's assume that this is our lowest level, we're going to have a larger or smaller and smaller number in the denominator. This means that n1 can be extremely large, right? Extremely large. As opposed to the fermions, always constrained to be smaller than 1. Here n1 can actually diverge. And we're going to use this property shortly. Yes, questions? You had questions.
You can also derive it from the equation when we calculated the partition function. We used the geometric sum formula. We assume that's the. We
assume that this guy, whatever we had, is smaller than 1. Yes, you're right.
So it's also from there.
Yes, absolutely right. Well, at least it's consistent. Any other questions? Okay, so now I'm getting to your G0. So this is, remember there is a great difference between, not small and marginal, but great difference between this n1 and 1. Because this n1 is also called the occupation probability, okay, for fermions. Occupation probability. Sometimes we refer to this quantity over here also as occupation probability. And in all the different calculations, previously we used this as what? As Fermi statistics, right? This is going to be Bose, and usually called Bose-Einstein statistics, okay? So this is Fermi statistics, this is Bose-Einstein statistics. Fermi statistics.
So Fermi-Dirac.
Fermi-Dirac, yes. You won't forget about Dirac. Important. You're right. Fermi-Dirac statistics. And this is Bose-Einstein. statistics. I don't like to use this Bose-Einstein or Fermi-Dirac statistics because it's like, let's memorize this formula and plug it whenever we compute something. I usually prefer to calculate everything from those principles of the partition function, and that's it. But if you prefer to remember, okay, bosons, I have Bose-Einstein, and I memorize this, and fermions, I have Fermi-Dirac, and I memorize that, it's also qualifies for great answer in the exam. Okay, so this is the result that we obtain for a single energetic level. Now, we wanted to compute not just the the average number of particles for a single energetic level. We wanted to compute the average number of particles for the whole system, which has 3 energetic levels, and we also have degeneracy. So remember, n, it is n1 average plus n2 average plus n3 average. Now, I can say the following thing. We know that n1, it is 1 over e to the power beta epsilon 1 minus mu minus 1. And n2 equals to 1 e to the power beta epsilon 2 minus mu minus 1. And then n3 average is 1 over e to the power beta epsilon 3 minus mu minus 1. So in total, n is going to be the sum of n1 and n2 and n3, but it's not exactly true if I have a degeneracy. So if I have a degeneracy, it is as if I have specific level with epsilon 1, and if I'm looking on particles with different spin, this is the same as treating an additional level which has exactly the energy epsilon 1, and it's going to have exactly the same average number of particles as the level with epsilon 1. So in total, we have to count this degeneracy in a multiplicative form, because it's basically saying instead of one single level, you have several which are exactly the same. So it's like multiplying the average number of particles for a given level by the degeneracy. So we have G0 n1 plus G0 n2 plus G0 n3. So the final result for the average number of particles is a sum. I goes from 1 to 3. You have G0 over here. 1 over e to the power beta epsilon I minus mu minus 1. Right? Great. We want to compute something else. For example, we want to compute the average energy, right, which is this. So we're going to compute the average of n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3, which is epsilon 1 and 1 plus epsilon 2 and 2 plus epsilon 3 and 3, etc., etc., etc. Any physical quantity we are capable of computing either by using probability and describing, so this is the probability of occupation and we are going to use it, or using thermodynamics by saying we have this ground canonical potential, let's take a derivative with respect to the interesting variable, mu, beta, beta multiplied by u, whatever you like, right? And you're going to obtain the result. I always prefer to use probability, but it's a matter of taste. Do whatever you like. So great. This is what we obtain from the 3-level system. The crucial thing to remember is this expression over here. Now what we're going to do is to say, well, let's look what happens if we have, as for fermions, the next example we treated was Fermi gas. We have an infinite number of different states. All the particles are not interacting, and all the particles only have kinetic energy. So this is what is called Bose gas. It's very simple to this three-level system. The only difference is that we have an explicit way to compute what are the different epsilons. Bose gas, again, we have energetic spectrum, epsilon, which is p squared divided by 2m. We only have, we only have kinetic energy. We're looking on particles that are sitting in a box of dimensions L by L by L. So basically the volume is L to the third power. And we're looking only on the particles that are somehow located, they have kinetic energy, and they cannot get out of this box. Okay. So again, the same picture as we have for Fermi gas. The energies, there is an energetic spectrum, but unlike fermions, different particles can occupy different energetic levels. Great. So if all the energies are independent, right? So the total energy is, we can go and count over the different energies that we have inside our energetic spectrum, count on all the different occupation fractions for each of the levels, right? And this is how we're going to compute our partition function. Okay? So Z, the partition function, is just a multiplication over all possible energetic levels, okay? And we're going to compute the partition function for each given energetic level epsilon. And it's important not to forget the G0, the degeneracy that we have over here. Okay? Yes?
Would the G0 be depend on the epsilon, on the energy?
All right, so you can say, if you want to get a complicated task, that the G0 is actually dependent on epsilon. But if you have a free gas, so your degeneracy is not going to depend on your energy at all. Right? So we do not use this, that the degeneracy depends somehow on the energy. You can have a system where the degeneracy depends on the energy, but it just complicates a little bit this multiplication. Great. So what is the next step? The next step is to compute something like the, well, this is a partition function. Let's compute, first of all, before we compute the potential, grand canonical potential, what is Z epsilon?
1 over E.
So Z epsilon is a sum, okay, a sum, and epsilon goes from 0 to infinity. So this is the number of particles that are sitting at energetic level with epsilon, e to the power minus beta, and epsilon multiplied by epsilon minus mu and epsilon. Like in the system with three levels, I care only about each specific level. I claim that all the different levels are independent. We have shown this previously, so then I don't have to prove it to you again. Okay. And the only thing that matters is how many particles are sitting at a given level. And we're just calling them n epsilon and counting on all the possible variations, meaning n epsilon goes from 0 to infinity. Now, it's the same summation as we have before. The sum n epsilon goes from 0 to infinity, e to the power minus beta, epsilon minus mu to the power of n epsilon. It's a geometric sum. So it is simply 1 over 1 minus e to the power minus beta epsilon minus mu. Okay. If we now want to compute the grand canonical potential, which is minus 1 over beta log of z, so this multiplication over epsilon turns into a summation over all the different epsilons, and we have a summation over log. So psi is minus 1 over beta, a sum over epsilon, log of z epsilon to the power g0. Okay, so we can take this degeneracy out, and we have minus g0 divided by beta, a sum over epsilon, log of z epsilon, and that's it. Now, since each of these z epsilon is what? Is 1 over 1 minus e to the power minus beta epsilon. So we have here g0 divided by beta, a sum over epsilon, and here we have a log of 1 minus e to the power minus beta epsilon minus mu, and that's very nice, but not sufficient, right? I don't want to now to count over all the different epsilons. Moreover, it's not countable. The spectrum is what? The spectrum of the energies when the energies are only kinetic energies, the particles are basically free and only bounded by my box volume V. The energetic spectrum is continuum. Okay, so the same claim was done for fermions. So instead of this summation over here, I have what? G0 divided by beta, an integral, and my energy can go from basically 0 to infinity. Later on we will see that it's not exactly 0 because we have a minimal energy. From 0 to infinity. Of what? Of a log of 1 minus e to the power minus beta epsilon minus mu. And what we have over here? D epsilon. What is this d epsilon? Density of states. For what?
For free particles in a box.
For free? No, for waves in a box. Right? Free particles. Well, you were right. Because in quantum mechanics, free particles are waves. Right? So what is the solution of Schrodinger equation for a free particle? It's e to the power minus kx. Right? Yep. So this is only sinus and cosines. And since the particles cannot escape out of the box, right? We have these boundary conditions where the wave functions, it basically zeroes out at the perimeter of the box, right? So this is why we have the density of states of all the different sinuses and cosinuses that can zero out on the perimeter of the box, basically standing waves, right? And we already know this, right? So the guy who calculated this was Debye for waves inside the media. Of course, he didn't know anything about quantum mechanics and Schrodinger equations and etc. etc. It wasn't existent yet. But since Schrodinger equation is a wave equation, the solution for d of epsilon is exactly the same. Okay. And we have already previously derived it. Yes?
Not really changing like from u to infinity and not or from
Ooh, an interesting question. Why from mu to infinity?
because then we had last 0.
Yeah, but so the point he's making is the following. Mu, as we already said, there is a condition that epsilon larger than mu for any epsilon. Okay. Now, usually what we have in a physical system, energies are given to us. So in our model, the energy is going from 0, not exactly 0, but the first excited state, okay, where and upwards, and we're not going to modify them. Mu is something that we can control. But basically, when we say that all our energies are from 0 to infinity, it means mu is negative. Okay? This is what it means. Because otherwise, you're right, otherwise we have a problem. The problem we already have on the level of the partition function. As we previously seen, right? We've seen that for any epsilon, epsilon have to be greater than mu. And since we're going to treat all the different particles that are going from 0 to infinity, we have to assume that mu is negative. Now, what is the d epsilon? V over 2 pi squared. No, we have something else. 2m h bar squared 3/2 epsilon to the 1/2. Yep. I think this is what we have. You don't agree with me? Do you remember this formula? Okay, so this is v pi squared. Here we have k squared, right? dk to d epsilon. Okay, what is e? What is k? We know that epsilon is k squared p squared divided by 2m, which is h bar k squared divided by 2m. So out of this, we obtain this expression for the density of states. Right? Last week, we've done it explicitly. Okay. Great. Okay, so now that we have the grand canonical potential, which is psi equals to g0 beta, an integral from 0 to infinity, log of 1 minus e to the power minus beta epsilon minus mu. What we have over here, v by 2 pi squared 2m divided by h bar squared 3/2 epsilon to 1/2 d epsilon. So this is psi. Okay, and the task that we want to obtain is what is the average number of particles inside this box. What is n? And we have half an hour, and unlike the calculation for z, we are going now to do explicitly this d psi to d mu. So what we are going to do is to take a derivative, nice derivative, okay, of this unlucky integral. Okay, so we have minus d to d mu of g0 beta. Let's take everything that is not dependent on anything, like mu or epsilon, out of the integral, which is v divided by 2 pi squared 2m divided by h bar 3/2. And here we have an integral from 0 to infinity log of 1 minus e to the power minus beta epsilon minus mu. Right? Epsilon to 1/2 d epsilon. Look, this goes out, so we have minus g0 beta v 2 pi squared 2m h bar squared 3/2 an integral from 0 to infinity, the derivative of a log with respect to mu. I don't care. I can take this this derivative and put it inside the integral because I assume that the integral converges uniformly, which means that it's 1 over 1 minus e to the power minus beta epsilon minus mu. I have from this guy minus e to the power minus beta epsilon minus mu. And the last derivative is what? With respect to mu. So I'm going to have beta over here. In addition, I have epsilon to 1/2, and I have d epsilon. Okay, so it is minus g0. Beta over here get cancels out. Something else is getting cancelled out. Yep. So d0 v 2 pi squared 2m h bar squared 3/2. Inside the integral, I'm going to have 0 to infinity. The minus is cancelled out too, right? This and that. So we don't have a minus. And I want to take this exponent and put it inside the denominator. And I have epsilon to 1/2 divided by e to the power beta epsilon minus mu minus 1 d epsilon. Okay, so let's call to whatever it is a. Let's call to zeta to e to the power beta mu. It has a special name. I don't know the translation to Hebrew, but in English it's called fugacity. And by using this, I have that the average number of particles is a, an integral from 0 to infinity, epsilon to 1/2, divided by this fugacity to the power minus 1, e to the power beta epsilon minus 1, d epsilon. Okay. So our final task is somehow to compute this integral. Extremely fun, right? You all like this. Okay, so fugacity, okay? So the translation of fugacity in Hebrew, fugacity. We will see what it means. When we have finished to calculate the integral, I will try to explain what is the meaning of this fugacity over here and why it's important. We'll see it in a bit. 20 minutes. All right, so now let's calculate this integral over here. Right now, how we calculate integrals usually. Right, so we push it into Mathematica, and it produces an answer. But the way it operates, it's not always a good idea. We usually, unless we see that there is some sort of solution, we want to, in a lot of cases, we want to express the integral as a sum, right? So as there are solutions of differential equations in terms of a sum of some functions, exactly the same goes for integrals. So in a lot of cases, we just want to describe this function as a sum of something, okay? And this is what we are going to do. So I'm going to translate this integral into the following form. This is an integral from 0 to infinity, epsilon to 1/2. And I'm going to write here the fugacity. And I'm going to write here e to the minus beta epsilon divided by 1 minus the fugacity e to the power minus beta epsilon minus 1 d epsilon.
No, not one. Without minus one.
Without minus 1?
Yeah,
No, with minus 1.
without.
Why? If I okay. Yeah, thanks. All right. The next thing is to look on this and we say it's a geometric sum. Okay. So basically, what is 1 over minus x? It's a summation of x to the power n goes from 0 to infinity. Okay. So we have this as a, an integral from 0 to infinity, epsilon to 1/2. Let's take the fugacity out. We don't care the fugacity. Okay, it's out. And here we have sum n goes from 0 to infinity of the fugacity e to the power minus beta epsilon to the power n. And we have epsilon 1/2 e to the power minus beta epsilon d epsilon.
You can just shift the sum.
I can shift the sum. I'll do it in a second. I want to do something else before I shift the sum. I want to say that epsilon is what we have, y squared. Okay. So epsilon is y squared. So we have d epsilon is what? Is 2y dy, right? And epsilon to 1/2 is simply y. Okay. So we obtain that it is a fugacity, an integral from 0 to infinity, because when epsilon is 0, y is 0. When epsilon is infinity, y is infinity. So the limits of integrals stay the same. Here we have y e to the power minus beta y squared. A sum n goes from 0 to infinity. Fugacity e to the power minus beta y squared to the power n. And here we have 2y dy. Okay. Great. Now, why have did this transformation? Because somehow I see that I have e to the minus beta y squared, and this is, I want to translate everything into a Gaussian integral, and Gaussian integrals we know how to compute. Okay. All right, so what? Let's see what happens. We assume that everything here is converges uniformly, so we can take this out of the integration. So we have 2a fugacity, a sum over n goes from 0 to infinity, an integration from 0 to infinity. Here we have y squared e to the power minus beta y squared e to the power minus beta y squared to the power n, and here we have a fugacity, and this is to the power n dy. Okay. Seems okay. Now I again try to perform the Feynman trick, because I look on this and I say this is minus d to d beta e to the power minus beta y squared. Okay? So I have 2a, I have a fugacity, a sum n from 0 to infinity, fugacity to the power n, an integral from 0 to infinity, minus d to d beta of e to the power minus beta y squared, e to the power minus beta y squared multiplied by n dy. Okay, I look on this guy and I use the Feynman trick again. So what's the Feynman trick for this? What do you say?
Stas, why didn't you take it together? Parallel.
Because now I want to do this.
F1?
What is this? So what is d to d beta? E to the power minus beta y squared
You got the same result.
n plus 1. I get the same result. Right? What is this? It is no. To the power of n plus 1. What is this? Is 1 over n plus 1 e to the power minus beta y squared to the power of
Then plus
n
in the denominator.
and d to d beta e to the power minus beta y squared.
Then plus 1 is in the denominator.
In the denominator, it's the power. It's the power of n plus 1. So it's going to be multiplying this guy by n plus 1. Fine. Right? What is this d to d beta of a to the sum power of n? Sorry, n plus 1 is going to be over here. That's what you meant?
Yeah.
Okay. Okay. So we are going to use this again and say, well, whatever it is written over here is simply 1 over n plus 1, okay, this derivative. So it is 2a fugacity, a sum goes from 0 to infinity, fugacity to the power of n, an integral from 0 to infinity of 1 over n plus 1 with a sign of minus 1, d to d beta of e to the power minus beta y squared n plus 1 dy. Okay, so the next step, let's take everything that's not related to y outside of the integral. Why? Because the integral always converges. So it is 2a fugacity, a sum n goes from 0 to infinity of minus 1 divided by n plus 1 fugacity to the power of n, right? d to d beta of an integral from 0 to infinity of e to the power minus beta y squared n plus 1 dy. Okay. So all of this was worth just to get this integral eventually. Why? Because we know how to calculate this integral. So it is the integral of 0 to infinity of e to the power minus b y squared dy equals to 1/2 square root of pi divided by b. Okay? So this is the formula. You have to remember this, and you need to know how to prove it. Not for the exam. But you will use it a lot. So in this class, in field theory, in condensed matter, whoever is going to get to graduate studies, the Gaussian integrals are the bread and butter of every physicist. So let's see. So we have 2a fugacity, a sum n goes from 0 to infinity, minus 1, n plus 1, fugacity to the power n, d to d beta. We have a minus over here. And eventually what we have, 1/2 square root phi. What we had over there is beta and n plus 1. Okay. The next thing is, almost the last, is first of all we can cancel out 2 and 2 over here. And the minuses, we'll get the minus in a second, okay? Because we haven't taken the derivative of a square root. But it's going to get rid of that. So we have minus a sum, n goes from 0 to infinity. Let's take the square root of pi over here. So a square root of pi. Let's take the fugacity now inside. So we have fugacity to the power n plus 1 divided by n plus 1 to the power of 3/2. And we have the derivative of this beta over here, which is minus 1/2 multiplied by 1 over beta to the power 3/2. Okay, so what we have, I'm sorry, so this minus wasn't there, right? So we have only minus 1 over here. There is no additional minus, so this is important. So we have minus, I want to cancel it out, square root of pi. This minus cancels out, so we have divided by 2. And we have beta to the power of 3/2. And we have a sum, n goes from 0 to infinity, of the fugacity to the power n plus 1 divided by n plus 1 to the power 3/2. Now there is such a nice thing that's called a polylogarithmic function. So f of fugacity of alpha is a sum r goes from 1 to infinity of the fugacity to the power of r multiplied by r to the power alpha. Okay? So this has a name, this is a special function called polylogarithmic function of order alpha. Finally, we obtain that the average number of particles inside the system is A. Do you remember what A is? I don't remember. So let's write it with the A, and then I copy the form that I have in my notebook. A square root of 2 pi divided by 2 beta of 3/2 f of 3/2 of the fugacity. Okay. Now I have a couple of minutes, so I want to treat this function. First of all, let's write it down in some other terms. So the average n, and here I just use whatever the values for A are or for beta. So we write it down as G0 V divided by lambda t to the power 3. And here we have f 3/2 of the fugacity, and lambda t, which is also called a thermal wavelength, it's just simply whatever is left from a and square root of pi and etc. So it is a square root of 2 h bar pi divided by m k Boltzmann 2. Okay, so seems like a very nice formula. Doesn't really gives any intuition because of this nasty polylogarithmic function. Okay, but yeah, we can calculate it, right? So we spent a lot of time, we took a derivatives, we used Feynman tricks, etc., etc., etc. We used Gaussian integration. Very nice. Not clear at all. What do we have over here? But actually, we have a fantastic result, which says that, well, something is going on here. Let's look on the behavior of this polylogarithmic function that we have. So this is f3 halves of the fugacity, and here is a fugacity. I remind you that the fugacity is e to the power beta mu. Okay. This function goes like this. Okay. Basically, the slope of this function diverges. Bad. One, this has a finite value, 2.61. Okay. And the slope is diverging. Now, we already start to understand something, why we should obtain some sort of divergency around fugacity equals to 1. Because what is fugacity? It is e to the power beta mu. So when fugacity equals to 1, goes to 1, it means that mu goes to 0. Okay. So mu goes to 0. We know that there is some problems with this number because we already stated that since we have energies that go from 0 to infinity, now the chemical potential mu have to be lower than any possible energy that we have inside our system. So some problems might arise when mu goes to 0 because our lowest energy is 0.
But we're in a box, so the minimal energy which is not.
Okay, so that's very, very close to 0. Okay, in the continuum limit it's 0. Now, great, but so the divergency can say, well, maybe it's rooted inside this function. Okay, so think about it. What is this f(3)2 of fugacity? It is a fugacity of to the power of r goes from 1 to infinity, r divided by r to 3 halves. And when we set fugacity to 1, it goes as a sum. R goes from 1 to infinity of 1 divided by r to the 3 halves. And something bad happened to this. Well, it actually converges. Okay, it converges, and it converges to this value 261, etc., etc., etc. But the fact that this function is converging to a finite value, it's a problem. So we do understand that there might be something really bad that happening when mu goes to 0. But you have to notice, and I will explain it in a second, that the fact that this function, this polylogarithmic function, converges to a constant value when fugacity goes to 1, it's a huge problem. Okay? Why it's a huge problem?
What's the difference between taking mu to 0 or taking the limit of high temperature?
I will explain it later. So when you have, so basically when you have beta goes to infinity, you have some other facts that are coming from here. But it will be clear in a second.
But mu is also dependent of t. Okay.
Mu can be dependent of t.
Yeah.
Okay. But just a second. Give me just a second. Look on this expression that we have for the average number of particles, which is G0 V lambda t F3 halves.
Lambda t to the zero.
Sorry?
Lambda t בשלישי.
Lambda t to the third power. Okay. So we have that n multiplied by lambda t to the third power divided by G0 V, here it's just the density, equals to F3 halves of the fugacity. The the polylogarithm. The polylogarithmic function, as we see from this plot, it's always smaller than 2.61. 2.61. So we have n divided by v, lambda t, those are constants. Lambda t depends on the mass of the particle, the K Boltzmann, the temperature, 2h bar squared, pi, controllable constants. N is the number of particles that I put inside the box. V is the side of the box. G0 is the degeneracy, 1, 2, 3, some integer number. And all of this is smaller than 2.61. How? Why? I can put an enormous number of particles inside a box. Why I am going to be obligated to say that, well, the number of particles in any box should satisfy this equation. This can't be true, because the number of particles that I can put inside a box is unconstrained. The density can be extremely large. I can modify the temperature. I can modify different constants. So it's not that lambda t is something very unusual and it's modified, or G0 or V. There is a problem with this restriction. Something went absolutely wrong, right? Either in our derivation, which you followed me and at least you agreed on every step of the way, or in some assumptions that we made. But so far, what we obtained from all this calculation and the grand canonical potential, etc., is that we have a restriction for the number of particles inside a given box, and this restriction cannot be true physically, because I can always push some other particles inside. Okay?
So for average number of particles, not for...
So what? So what? I can put another bunch over there, and the average will grow.
But the number of particles is not constant.
You remember what we have done in the fermions? I assume that the number of particles is constant, and therefore mu can be modified. The same goes here. I assume that the number of particles in the box is almost constant. It has some small variations, but it's almost constant, and I can always increase it. It's going to modify mu somehow. Who cares? Think about it physically. I can always push more and more and more particles inside the box. At some point, maybe it's impossible, right? But it's definitely not at this limit. That's what I'm saying. So something went absolutely wrong. Now, and we'll see what exactly went wrong. It's not the integrals. It's some very small assumptions that we made along the way, right? We'll see it on Tuesday. By the way, next Sunday there will be no lecture, and instead I'm going to give the lecture on this Wednesday at 8:15. It's going to be transmitted on YouTube live. Sorry about that. Sorry? 301. I will publish an announcement about that. And see you on Tuesday.
תחזיק עד יום שלישי.
תחזיק עד יום שלישי. שמה? שאני אעשה את השלמה.